Here, sound check. All right.
Okay, welcome back, everybody. Hopefully, full tummies now. So I'd like to welcome Brian Hubbs with RDH Building Design, Facade Risk Mitigation. Brian, welcome.
Thank you. All right, I'm going to give 1 more minute for everybody to get back in here and close those doors. There's still a lot of people out there. All right, thanks for coming to see me today. I present a lot. I'm sure some of you have seen me present before, so I cobbled together all the kind of interesting fenestration case studies that I've got on my plate these days, and sort of threw them together real quick. We're going to burn through them. It's like TikTok death scrolling for fenestration people. So it'll be fast and furious. Then I'm going to drop the mic and try and catch a flight. So let's do this. Okay, yeah. I love answers. I'll try and leave some time for questions. All right. Disclaimer, standard. Agenda, a bunch of random case studies, fenestration. Let's do fundamentals first. This is from a presentation I gave at Zach World of Facades this year. This is something I've seen real recently. A bunch of performance mock-ups fail because people didn't understand how their system was moving. And we were doing some pretty intricate things with the building. And it had intricate things like balconies and features. And they were moving differently than the fenestration system. I don't know if many people here in the room have done performance mock-ups, but when you do go to Asia or Europe or Montreal to do a performance mock-up and you don't pass it, it's a $500,000 deal. And there's been a couple that haven't passed twice. One of them is a case study here I'm going to do. So I think it's really important that whenever we build a building, I always start from first principles, right? How's that building going to move? And we live in, the Cascadia Fault. So there'll be a big one at some point, 9.8. So we have very high interstory drifts in Vancouver. So when we bring systems from Eastern Canada, Europe, Asia, some places in Asia, they often aren't tested to that same level of interstory drift that we experience here. As luck would have it, I just got back from New Zealand. I got a chance to tour around Christchurch, where they weren't expecting an earthquake, and they got a 6.7. And a great deal of that city is still not being used. There's buildings sitting there that are cracks every foot all around the building. They're glued together just to stop them from falling over. So it hit me pretty hard. That's a 6.7 is a pretty big earthquake. That one did 1G left and right at the same time, because it's a subduction zone like ours. It did 1G up. That's like taking the earth, flipping it over. It's like hanging the building from its foundations. So it went up, over, and down in another spot. And that's what caused all that damage. So it makes me think about my own house and the building I work in, and a lot about the buildings that we build. So in Vancouver, you're typically looking at interstory drifts between 50 and 75 millimeters for the big one. That's a sort of serviceability is about 25, about an inch each way. And then the one that, the important one is the one that stops everything from falling off the building. That's 75 each way. So 3 inches each way. 1 story. If you have 2 stories, it's double that by story. And you also have to take dead loads. So there's a bunch of different vertical loads that you have to account for. Long-term creep, initial deflection due to pulling the forms off and having it just deflect due to dead loads, and live loads. All these things need to be accounted for over the life of the building. Typically, you're looking at numbers around 1 inch for that. So you need to allow that to move if you're putting a fenestration system on or in a building. There's kind of 2 different ways of thinking about putting a fenestration system on or in a building. Some kind of curtain wall approach where you hang it from the slabs, and it's usually hung from the slab above, and then over down to the slab below where there's a wind anchor, stops coming in and out, but the dead load of it is hung from the slab above. And a window wall, punched window, typical wall approach where the system sits on the slab and rides with the slab. Those are going to do different things. And I'm out. I'm in. I lost a lot of my battery, maybe. Check. Okay. I've had some buildings where they combine those two things into one building. That's difficult because you have an interface where some of it's riding with the slab below and some of it's riding with the slab above, and you have a whole bunch of weird movement happening at those joints. That also happens at balconies and things like that if you're not careful. So when we're talking about movement, all things we put on or in a building are going to do one of three things. They're going to rack, which is your like stick-built curtain wall way of thinking about it. The whole system racks and turns into a trapezoid. It comes back to a square or a rectangle. Rotating, where the whole system rotates. And translating, where it slides back and forth. A lot of people look at curtain wall and go, yeah, it translates. That's what the interlock's for. It's for translating. In effect, if you're talking about unitized curtain wall, almost never translate. They almost always rotate. And you're not going to really know about that unless you've really thought through your design and watched it actually go through one of these performance mock-up tests. All right, so here's a good example of a window wall system, locally manufactured, that is translating. Okay? Almost all translation, but can somebody see any rotation? Right? Because things only translate to the corners. When you have interior and exterior corners, you've got to rotate that. You can't translate that, it'll just break off and fall on the ground. So you need to design joints in there that can translate where you want it to translate and then move into rotation at things like corners or other things that aren't moving with your system, right? Here's a big panel approach. Almost all big panels. This is Intelligent City's first mock-up for a CLT. This is, I think, a 20-foot. They make 20 and 40-foot panels. And you can see here, they've got to translate because you can't rack the CLT. It's too stiff. And you can't rotate it because it's way too big. If you tried to rotate that, you'd have a ton of movement and it would break something up above. So the only way to do this is to translate it, and then at the corners, build in a mega joint. That's a 4-inch silicone joint hidden behind those panels that can take that movement, come back, and still be air and watertight. But you have to think about that before you get to this point. This is in and out. So you can see it, we move it the other direction. You can see what's happening there. Pure translation with rotating corners. This is your classic unitized curtain wall. By the way, do this. If you're ever doing a performance mock-up, set up a bunch of GoPros and record what's happening, because you can't really see this because it's very slow. They're using hand pumps usually, and you really can't see much movement until they're done moving it, and you really don't know what's happening. So put some tape markers on critical points, stand back with some GoPros and record it, and then speed it up 30 times, and you can start to see what your system's doing, any pinch points, how you might want to tweak the design to be more efficient, that type of thing. So that's classic rotating curtain wall. It's not racking, it's not shifting. You want them to end up in different spots after this test because they have to come back together so the gaskets all meet and it's air and watertight. They don't have the ability to move a lot and still be air and watertight. They got to rotate. Well, what, you ask, if you've got constantly shifting balconies? There's a couple of projects like this in Vancouver where balconies shift randomly, right? And if you're using curtain wall on this, you're hanging the curtain wall from the slab edge there, but then you're probably going to support it on the slab edge at these balconies, and then you're going to probably have to hang it from here. So you're going to have all kinds of weird movements happening, and you got to make sure that if you do have that, it stays together, it's air and watertight after it moves, and nothing falls off after the big one. You end up with, so here's where we're going to figure out how we're going to make those joints work and go around these constantly shifting balconies and how we're going to attach it. And we end up with this. This is the third attempt, because the first two failed, of the Franken mock-up. It's racking and it's rotating and it's translating, and can you see it's all in different spots, right? So this was incredibly complex, incredibly expensive to get this to work. Much more expensive than the curtain wall manufacturer it dreamed of, because the installation costs were so high. So you can do it. It's not simple. If you'd have built this out of window wall, it would have been very simple. Everything would have sat on the slab, and there wouldn't have been all this differential movement. So sometimes window wall's better. What's a pass? What's a fail? We talk about interstory drift, right? Well, there's two criteria, right? The 30 millimeters of movement Nothing can bend, break. There can be no permanent deflections, and it has to be air and watertight after. And then this is after the 30 millimeters of movement or the 75 millimeters of movement. And then stuff can happen, but nothing can fall off because you want to be able to get out of that building and run away from it just after your earthquake. And you've seen the pictures of the earthquake last week. Pretty scary. So you can see here, we've got a bent anchor, we've got bent flashings, got cracked glass, we've got some wood curtain wall torn apart here at the corners. That can happen, nothing can fall off, right, for the big one. And that's okay. You'll be pretty happy if we have a 9.8, nothing falls off your building. That's not really realistic downtown because there's lots of buildings built before these codes were in effect, right? Okay, switching topics randomly. What IGU standards and labels are required by code? Murray. Let's wake you up. You know the answer to this. All right. No, part 9. Part 9 says, okay, and the reason I'm saying this is I look at a lot of failed IGUs and I look at a lot of buildings that require complete IGU replacement after not that long. Many times when that happens, those units don't meet code. So I'll simplify it. In order to sell an IGU in Canada, you need to conform to CAN CGC 12.8 or the harmonized standard with the US, ASTM E2190. Done. Simple. Okay? How do you know that your units conform to that? That's the key. There's a little certification agency, right? IGCC and IGMA have a certification agency that lists all the certified product out there. So if you're using IGUs and you want to make sure they meet the building code, buy a certified product and check the certification certificate to make sure it's current, that it's the right plant, and that it's the unit that you ordered, okay? That's how to do it. There's their IGMA, there's their IGCC certificate. It's for Oldcastle's Langley plant, and these are the units that they're certified to make. If they don't make these units, and this is all, this short form legend when you go on their website, you've got plastic hybrid stainless steel spacers, loose fill desiccants, PIB silicone, it's all laid out there. It's all been tested. It takes several months to do this testing. So if you start a project at the time where you're reviewing shop drawings and they haven't got this certificate yet, chances are you'll have product installed before they get this test done. And you're taking some risk there. So if I have to say one thing, specify and buy certified product from certified manufacturers, and then you don't have to think about it anymore, other than just to make sure the unit that you're asking for, if it has argon, if it's got capillary tubes, if it's got other things that are abnormal, offset edges, that it's actually still certified. Easy to check. Easy to check for regular units, a little nuance for other ones. But it's incredible because if I'm on a project where we got a lot of IGU failures and I look and this isn't done, and I start to look and those units haven't been tested, they don't meet code. You just built a building that doesn't meet code. So don't do that. And a lot of the ones I'm seeing failures on haven't been tested and aren't certified. Some of them are. But when you're buying offshore, there's manufacturers that don't know what 12.8 is or 2190. So locally manufactured certified product is lower risk. Case studies, mass wood. Let's switch directions again, talk about mass wood. All right. Airtightness of mass wood. So you guys are in the fenestration industry. You put fenestration into mass wood buildings, and the mass wood likes to stick out around your fenestration. And there's the things you need to know about because your product is very well tested. You go through great pains to test it and have labels on it. Mass wood, not so much, right? It's tested for things like strength, but not necessarily for airtightness. It's somebody else's job to figure out how you make a system out of that. And so, here's some shots here of a CLT roof wall interface, and that's air leakage I'm seeing on my thermographic camera, right? Coming through the unsealed joints between the CLT members, okay? How does that relate to fenestration? Well, you're going to put your window your fenestration product into an opening, and there's going to be wood on either side, and there's going to be wood up top. This particular one is so it's a nail lamp product, so it's basically just 2x6s, 2x8s nailed together into a slab. That's what it looks like after construction. When I scanned that, they were having icicles, and the flag in the building, the flags that were supposed to be, in the building not flying, were actually flapping in the breeze. Why is it doing that, Brian? I come out, we do some smoke testing, some thermography. It's pretty obvious. There's air leakage over and above top that fenestration product around it. It's a problem. So, being fenestration people, we need to help the guys that don't do testing all the time on their product like you do, and make a system that works. If you're interfacing with this, raise an alarm bell. Say, my product is 0.1 liters per second per meter squared at 75 pascals, and that's 100 liters per second at 75 pascals. There's a mismatch here. So something that I've found out more, I've always known this. We've always known this in the leaky condo industry, right? Time of wetness is the thing that matters. If it gets wet and dries out really quick, it's okay. If you open up a condo and it's all rotten and it's dry, and they call it dry rot, that's not really dry rot, that's wet rot, that's rotten, and then dried out afterwards, right? But as we start to think about wood now in taller buildings and more complex buildings than our standard leaky condo or standard wood frame condos.
Opportunities for improvement.
Oh yeah, there's opportunities to do it again, right? So that, this is a building, this is terrace house. We never built it, thank goodness. But the architect on this one really wanted wood in their shadow boxes, right? Anybody put up your hand if you think wood in a shadow box is a good idea. Why? Murray knows the answer to this one. What's in a shadow box other than air? Yeah, there's sun, there's UV.
And there's shade, so you're going to have wet.
It's going to condense in there, exactly. So time of wetness is an unknown. How long is that going to be wet? What's it going to look like over time? So I kind of stepped in and said, this is probably one of the worst ideas I've ever seen, but I don't want to do it because if we do, we're gonna have a problem. I've never really seen a shadow box that doesn't have almost permanent condensation all winter. That's why we use frit, so you can't tell, right? So I convinced the architect that if we had these, he gave me a piece of wood that he wanted, I would scan it in and have a 1080p color frit printer printed on the back side of the glass. And if we could fly to China and have it set up, if he could choose which one he liked the look of better. And so that's what that ended up looking like. This is a sort of a Brian makeshift viewing platform, i.e. a forklift. I had it up high, couldn't get too close to it. And I had one down here. That's the piece of wood that he gave me. That's the scan of the piece of wood. Which one looks better? The scan looks better, of course. And that looks better initially. Think about 10 years down the road when that piece of wood is black and full of mildew. It's going to look way better then. So, so this is what wood likes. This is what wood looks like if you leave it exposed. This is the roof of our Victoria office. We just have tons of different samples of different kinds of wood sitting up there in the sun and rain, just watching how they age, right? So this is what a Koya looks like new. That's gradiana pine that's been treated with a acetylated process. It's a great process, heat and acetic acid. That's what it looks like after 16 months, roughly equivalent to our untreated hemlock, right? So don't think that just because it has a treatment means it's going to last forever and look good forever. You need to look at what it's really going to do. And if there isn't anything on the internet, call me because we've got everything on our roof we can show you. We take pictures of it every couple months. We've got a log. It's for our use only, but I'll share it if you ask me a specific question. All right, here's my favorite one. Mass wood is not curtain wall, right? This is a very high building, very good looking building. And my client here is the curtain wall manufacturer. He makes this curtain wall. I've been to his performance mock-ups. I've built many buildings with it. It's very high performing, rain screen, unitized curtain wall. It's some of the best stuff on the market. So I was surprised when he called me and said, they're saying my curtain wall's leaking. So can you come and figure out what's going on? I said, sure. So I bring out our rain rack and our smoke gun, and we just go out and take a look at it. And I'm just, I hadn't started testing yet, but I'm like, maybe this piece of wood that goes from inside to outside, that's checked, that faces the ocean and is only 100 yards from the ocean, is leaking. And maybe it's not your high performance curtain wall. Sure enough, we did some water tests, and you can even see here, you got, oops, I don't like this clicker. You can see here, we had water draining out between the bottom of this and the curb on the inside. I poked a hole in it, and then the water just flowed in. So they had kind of caulked this from the inside, thinking that it would hide the problem. What's that really going to do, Murray?
Finger in the neck.
It's on the wrong side. So that's going to be nice and moist under there, and the end grain is facing down, and we know what happens when wood is 100% humidity for its lifetime. The lifetime is shorter. Mass wood can be an integral part of fenestration system if you do it right. My favorite way of doing it these days is using a system like this. This is Rayco's. This is Blackcomb Glass's cool structure that they're doing. And you keep the wood on the inside where it's dry and warm. You put something rubber that's completely waterproof. In this case, we got Rayco to switch to silicone. So they have 100% silicone gasket there that we can weld together with silicone. And we can make very complicated shapes. Rafter into purlin into rafter gutter drainage system that drops down. It works really well. We use this system on Oak Ridge for a skylight as big as this room that sloped at 2%. We never had any exterior gaskets on, and it never leaked for several months in the winter when it was pouring rain. The water was just pouring off. So there's ways to do it. And all the ways to do it that are going to work, keep the wood warm, dry, away from the UV, inside. And put everything outside that's going to get wet, exposed to UV, make that silicone or aluminum. Right? Or steel. Make sense? This is my unofficial, accidental mass wood exposure nomograph. So if you want to figure out what overhang ratio you need, go out to UBC and look at this building. It's perfect. Right? It's got lots of overhang up here, and the wood looks good. It's got less overhang down here, and you can see it's not really raining that. It's not very windy this day, but water is coming all the way back here. So you can calculate the overhang ratio and say, let's not exceed that. At the base of these columns, you can see it's starting to deteriorate. And then over here where we have no overhang, we can see what that looks like after only a few years in service. And there's permanent damage to that assembly. It's not much longer for this world, right? It needs to be remediated or retrofitted or replaced. So this is a great little thing to refer back to if you want to know how much overhang you should put over top of your mass wood to stop it from getting wet so that it'll look good and it'll perform. I like it. All right, let's talk about spontaneous glass breakage. I'm seeing more and more of this. And there's lots of contentious rhetoric in the industry. Everyone knows what that is? Most people? High-rise buildings, several of them now, 4 to 30 glazing units in the first few years have spontaneously broken for no reason whatsoever. In one case, occupant showered with broken glass while he was sleeping. Other cases, it falls out onto the street, which is really bad because when people see that start happening, they start questioning occupancy permits and things like that. All the glass was fully tempered. This is what the breaks looked like when they didn't fall out. We basically go to the break point. The breaks will all go to one point. At the break point, there'll be a little butterfly. And on the edge of that butterfly, there'll be a little metal inclusion, if it's a butterfly. These are some cool pictures I've taken of those inclusions. That's a nickel sulfide inclusion right there. That's in a piece of unbroken glass. I got that. Not many people do. You can see how big it is. It's 0.5 millimeter. Usually, the ones that break glass are between 0.1 to 0.5 millimeters. So this is a big one. You can see here the stress concentration at this piece. This was a piece of laminated glass that broke due to nickel sulfide inclusion. You can see how much stress is still around that inclusion. It broke, it's still stuck in the glass. This was the hardest one for me to figure out. It took me a couple hours because there's no inclusion there, but I took many pictures from many different angles. You can see this break stress line here, and you can see the crack going this way, right through this centerpiece. This is actually 2 air bubbles. The blue is some dye that I put in there to try and figure out what was going on. And this is where the inclusion was. You see how it's kind of rough? It looks like that surface there, a little bit rough. And there's an air bubble on both sides. So that was an inclusion that broke the glass and flew out, and I never found the inclusion. Other things that you find in glass when you're looking for inclusions, refractory inclusions, they don't cause damage, they just look bad. Air bubbles. Those are things that you don't have to worry about. Right, so nickel sulfide inclusions can break spontaneously. The way they do it is that when you temper glass, they go into a high temperature state, which is slightly smaller crystalline structure than its low temperature state. Over the next few years, it will slowly revert back to its low temperature state, which is bigger, expand in the glass and break it. So if that inclusion's in the tension zone and it's big enough, it will cause the glass to break. Usually they peak 5 to 10 years in. There's been inclusions that have broken glass 20 years out, but they're rare. So I'm going to just go on a limb here and do some anecdotal stuff, but I see it more often in offshore glass than I do in glass from domestic and China, or sorry, domestic and Europe. And the reason for that, I see the frown. The reason for that, I think, is that most glass from, there's a lot of glass domestically and a lot of glass from Europe that gets heat soaked whether you like it or not, if it's tempered, right? Eckelt glass, I was there, they heat soak everything that comes out of their factory that's tempered. So I think that had a lot to do with it. Anecdotally, I've heard that low carbon glass that has a lot more recycled glass content has a slightly higher incidence of this happening. So if you're speccing that, maybe heat soak it because there's increased risk. For handrails, consider using heat strengthened laminated glass instead of tempered. If tempered safety glass is required, make sure you heat soak it, especially if it could fall off the building. If it's a door on a balcony and you don't heat soak it, the worst case scenario is that you replace it. If it's glass over the street and there's the Calgary Stampede underneath, that's a whole different risk matrix. Heat soak it, or don't use tempered. Use thicker heat strengthened glass. Heat strengthened glass has a very rare chance that it'll ever break due to nickel sulfide inclusion. I've only seen one in my entire career, and when I tested the glass, so they had actually over heat strengthened into the tempering range, and that's why that one broke. So if you're gonna do that, and you're gonna go through the process of spending $500,000 on a job to heat soak test all your glass, when they heat soak test the glass, they put it in a kiln, and they heat that kiln up and for about 2 hours, and that makes that inclusion revert back to its low temperature state and break the glass. So when you heat soak test glass, you're breaking a lot of glass that may or may not actually break on your project at some point. And you're also spending a bunch of money to put every piece of glass in a kiln like this. Not a very big kiln. Some people have bigger units, but it's a labor intensive and energy intensive process that results in you breaking some of your product and having to order new stuff. So nobody likes doing it. And that's why it costs so much. So if you're going to go through the process of spending the money, you might as well make sure that it actually is heat soaked. Most of the labels you see on the glass, they'll say heat soaked. Those are done with a frit when the glass is tempered, right? The frit is put on when it's tempered, right? Your frit mark. Not when it's heat soaked. The heat soaking comes after the label goes on. So just because it's got a label doesn't mean it was heat soaked. So there's a little product here that I've been recommending for people that are using high risk tempered glass or monumental tempered glass that's just too expensive to ever replace. It's called a heat soak test pen. It's called a check marker pen. You put it on the glass, it goes on purple. You heat soak the glass, it turns white. So now the factory can tell which units have been heat soaked and which ones haven't. Then you wash that off and it becomes clear. You can't see it anymore. And then if you ever want to know if it's been heat soaked, you shine a UV light on it and it lights up. So if you're going to specify heat soak glass, you may as well just use these markers. They're not expensive. And then you have a legal way of figuring out if it's been heat soaked. Cool thing, in the last month, there's been a paper published by Saint-Gobain that it outlines a method to figure out if your nickel sulfide inclusion has been heat soaked after it's broken the glass. So there now is a method to figure that out. So if the glass breaks and you find the inclusion, you can actually have it tested to see if that had been heat soaked or if it hadn't been heat soaked. And, probability wise, it hasn't been heat soaked if it broke, because the probability of having one is so small if you heat soak test. Guys having fun yet? Unsealed capillary tubes. Who uses capillary tubes? A couple people? Yep. This is many jobs. This is just a picture of one of them. 5-year-old building in Portland, hired by the contractor, architect, and developer to figure out what's going on in this building. They were alleging a bunch of things wrong, but one of them was there's a bunch of failed IGUs, and the plaintiff was claiming that the weep holes caused it because they were plugged. Okay? So we get brought on board. There's not very many plugged weep holes, but there's quite a few failed units, and they're not correlating. So we know that weep holes are not what's causing these units to fail. So we go out there, we have a little machine called a frost point tester. We measure the dew point inside those units to figure out if it's what it should be, which is minus 45 or lower for a brand new unit. And we find that it's not minus 45, it's minus 3, minus 2, 0. So we know there's a lot of moisture in there. Desiccant at its saturation level will produce numbers like this. So we know the desiccant's full of moisture. It's never going to dry it back down to minus 40. You're going to have condensation inside the unit all winter long, essentially, in Portland. And the other thing we did is we correlated that with fingerprint patterns, spotting patterns that we're seeing on the low E coating. So our thought was that the moisture in there was starting to corrode the low E coating. So we wanted to correlate the dew point with that, and we were able to do that. So here's your culprit. These got put in. These capillary tubes didn't get crimped, sealed, or anything. And as a result, every time the barometric pressure goes up and down, it pulls air in and out of that unit. And in short order, in a couple of years, that saturated the desiccant caused these things to fog. The other thing, this is from other jobs. There's some rhetoric about how you don't need to seal capillary tubes because water can't flow through them, and there's very, very low amount of things moving through it. Here's a picture here of water flowing through a capillary tube. So seal them. If you use them, make sure you crimp them and seal them. But crimp them and seal them, try to do that in the factory when you're making your unit, not on the job site when there's yahoos installing your product. Because this is another job, we replaced half of the units on this project, and it's a big project. This is where a capillary tube, I guess, was on the wrong side. So they pulled it through the seal over to this side. Here's one here where in the act of crimping it on site, because these got put in as unitized curtain wall with a little tube hanging out, and the guy would grab that tube with a Leatherman and twist it and try to kink it and cock it and stuff it back in. We got the end sealed, but pulled it out of the seal into the unit, right? So I see a lot of failed IGUs related to capillary tubes. I think if you have to use them, you got to be really careful. And if you do, make sure they're IGMA certified, right? With capillary tubes, with the method that they used to crimp them, because that's not included in your standard IGCC test. And then make sure that you try and do that in your factory. So you bring them to Vancouver, you put the glass into the frames, and then you have skilled people in your factory, only maybe one or two of them, that carefully crimp it and carefully seal it in place, and not random people on site doing it that you don't have no control over. Okay, this is something I'm seeing more and more of for good reason. We're building more modern buildings, and we're using a lot more solar shading, right? When you build a passive house, you're going to have solar shading on it. That's part of how a passive house works. That's why they call it passive. It uses passive things in order to control the heat that's coming in your building and the heat that's getting reflected from your building and not coming in your building, so that you're comfortable without using a lot of mechanical interaction, right? 1500 watt hairdryer heats a passive house. right? You don't need air conditioning in a lot of passive houses because you're controlling things like hot sun in the summer or shading devices, right? So this building, everybody recognizes this one by the IKEA in Coquitlam. Boom, we got lots of thermal stress breaks. We know it's a thermal stress break because it's 90 degrees on one side to 90 degrees on the other side, and it goes straight across or it veers out, but always at the edges 90 degrees. And because they always happen directly underneath a solar shading device, which is shading part of the glass and allowing full sunlight on the other part of the glass. There's some good sources on the internet. Vitro's got a good one. Almost every big glass manufacturer has a reasonable chart. When you look at the big things that add stress to your glass, thermal shading devices on the outside and blinds on the inside are the two big ones, right? They can double, triple the stress in that glass because of the temperature differential. Other things like low-E glass, framing systems, they all can impact it as well, but they're usually like very small factors compared to the big ones. And so if you've been ticking along, producing product for many years, it's never had a problem with annealed glass, and you're doing a passive house, and it's got lots of solar shading devices, you want to have a look at it for risk because you're doubling or tripling the stress that glass had in it that worked many years for you. A 28-degree difference in Celsius can break annealed glass. If you heat strengthen the glass, it's almost never going to break due to a thermal stress. The only... Can you fix the mic, please?
You turn this way.
All right, I won't turn that way. I can't because the screen's that way. All right. So the only time I've ever seen heat strengthened glass break due to thermal stress is when it was in a shadow box with a frit on it, touching the insulation. And there you can get 200 degrees difference between the edge and the center. And the frit actually kind of weakens it a little bit on that surface. And so if you're doing that, you need to use fully tempered glass, but don't do that anyways. Just use a rain screen. Have a vented space between. Anisotropy. I always have a hard time saying. So these are often known as tempered glass, quench distortions. This is what they look like naked eye. So these are a couple projects that we're on. We're seeing this difference in shading at high angle sunlight, right? This one's curved glass, and you can see the dark and light streaks, okay? So this is one here where this is using a polarized filter to enhance those, because what you're seeing is the stresses in the glass using a process called cross-polarization. And when you have high-angle sunlight on a blue sky, you get polarized light, and you can see it with the naked eye. It really enhances it to look at it with a polarized film. But you can see here differences in direction. So this glass has been installed 90 degrees to the tempering oven and 180 degrees to the tempering oven, and it makes it look much more noticeable. So we want to try and avoid that. This is a good example here. So this is no filter. You can see slight shading differences. With a polarizing filter, you can see the anisotropy. Curved glass, laminated curved glass especially, will give you very high anisotropies. This is some laminated glass, right? And you can see how that polarizing filter is affecting the glare coming from that paving stone. So what you're getting is polarized light off that reflection from those pavers hitting this handrail, making it look not great. So there's some new material, there's some new equipment you can buy for it's really, really expensive. I went to see this when I was at BOW this year. A haze scanner. The Europeans have made a standard called DIN 18198, and it has different levels, right, of distortion that you're allowed. This scanner will automatically look at the glass, look for anisotropy, and it will look for haze, and it will convert it to B and C. If it doesn't work, you just take the piece of glass and you put it back through again until you get it to work. Pretty slick. So for monumental glass, very iconic buildings, this is something you want to think about and look at. I don't know. I'll keep going. I'll just talk louder. That machine will also catch things like, this is on the left-hand side here, that's a haze cloud in laminated glass because it's not been properly vacuumed as it's been put through the autoclave. There too are some real iconic, huge pieces of glass in a fin wall that have, they call them skunk marks, but this is a damage from the because the glass cupped in the tempering oven. Can't see it. If the light's right, you see it. That haze scanner will catch that, right? And when you're talking about big pieces of glass like this that are impossible to replace or very expensive to replace, it's worth putting them through that scanner to make sure you don't have these things. And this is on the interior light of a triple. So you can't even polish that out. If it was on the interior light, you could take a machine and polish that glass out and make it look good. You can't if it's the inner light of a triple. This was SADAC's booth at BOW this year. They had a big polarized light sunglasses you could look through, and typical tempered glass on one side and their tempered plus on the other side, which has a modified tempering oven plus this scanner in line. So you can do it. So if you want to do it, you got to include that DIN spec in your spec and then make sure they make it in a factory with that scanner. Otherwise you can't. I don't think there's much else that can actually convert, a pattern to a standard like that. Here's one here, climatic load deflection. So this is, back to capillary tubes, right? You make the glass at one elevation, you move it up or down, right? You either pillow or you convex the glass. You can do things like modify your structural design to have less pillowing or convexity on the outer light by changing the stiffness of the two different layers. You can select a glass plant that's at a similar altitude to site. I think that's the key. Like, that's the easy one. Just, if you're in Vancouver, choose a plant that's in the Lower Mainland, and you don't have to worry about this kind of thing. Some manufacturers that are at different offer like a pre-pressurization, so they can put argon in at a pressure or at a vacuum, which will ultimately give you the right number when you're here. That works. There's two ways to do that. One is a tube. Don't do that. One is a machine that is a complete argon purge machine that is designed to do that. That's the one you want to do. You don't want to see people with tubes and a pressure gauge filling argon up. Like, that would be, well, I've seen it done. Don't do it. Site crimped and sealed capillary tubes are not recommended. Do it in the factory or don't do it at all. There's other ways that you can control this. This is a good one. You'll get a laugh at this one. Failed perimeter seal, low E coating failures. So there's a building we looked at, full building. These units are all in various stages of failed. And this building is only 10 years old. So we do a due diligence inspection. We look at it. We're trying to figure out what's causing this failure. We're poking around. We're looking at how they're made, doing some dew point tests. And I just poke my ruler in. Oh, no. Oh, no. So that's bad, right? There's not an IG on the market that can take that. That's not just sitting in a little bit of water. That's a hydrostatic head of about 3 feet of water. So that's a lot of pressure pushing water through that edge seal. So we had a look. Why is that happening? That should not happen. This is a rain screen curtain wall system. So we started to look, and it is it's structurally glazed. It's got a drainage cavity. It's sitting on setting blocks. It's got weep holes. Why is this not working? This should work. So we take a look. Oh, uniformly, this joint's not sealed at the top corner. So anything running off that goes into the glazing cavity, not down to the stack below, right? So it's supposed to go off here and then down here to the stack below and go out. But instead it's running off here and going in here, which is the space glass and the frame. And then when we hit the bottom of that, boom, we got a little plug. So they brought this sealant out here and plugged this corner so water couldn't get out. So all these units had water at the edges built up and failing you. So again, this is one case where the system design of the curtain wall impacted the longevity of the IGU. Weld spatter, that's a big one. Just damage in general to the fenestration products after you've left the site and put them in. So lots of weld splatter. This is a steel building, so lots of welding going on. This is a waterborne spray roller applied temporary coating, and the weld spatter just ate through it like it wasn't even there. So didn't work. We were able to kind of measure the depths, though only 5 to 8 mils of weld spatter depth, able to polish that out, take it down a little bit. We ran a structural analysis on it, make sure it wasn't going to impact the strength of it. So found out that was going to be okay. We worked, and they end up getting all that weld spatter off and looking good through immense amount of effort in polishing all the glass. But it's still cheaper than replacing it all. It's a quiet room. Ask me a question. Yes. Yeah.
So you seem to indicate that, heat soaking pretty much takes care of spontaneous breakage. But I've always been told, the age-old rule, 7 to 9 lights out of 1,000 will break due to nickel sulfide inclusion. Heat soaking reduces that to 3 to 5 lights out of 1,000.
That's based on an old Viricon warranty that was written by a lawyer, so they would never have to pay out on a nickel sulfide warranty.
Indeed, it's a liability issue, no doubt.
If you look at Casper's work, widely published, he worked for Senko. In his last few papers that he wrote, it's by ton, not by unit, because it's probability. But the way that he designed the heat soak test was that he wanted on a building, and I can't remember how many units, but it was on a high-rise building, he wanted to have less than one break on that whole building. Like I can't remember what the stat was, but it's like 0.2% chance of one breaking. So that's the number. If you're getting 30 breaking, you either had glass with way too many inclusions in it to start with, and you have thousands that broke in the heat soak chamber, or you didn't heat soak it. So yeah, there's some really good stats on that. Yeah.
Quick question: you ever seen any low iron break spontaneously?
Yes, and I actually fell for it. Fell for the. Don't worry, low iron. The process actually takes all the inclusions out, so you're good. And on that job, we had quite a few breaks. Yes, but it wasn't like European low iron. This is lower iron from another place. So. Mid iron, yeah. But I fell for it, and I regretted it because it should have been heat soaked. Yeah. If it matters, heat soak it. If it doesn't matter, don't. That's my rule of thumb. And if it and matter means if you're over top of the Calgary Stampede in the summertime when it's hot and sunny, heat soak it, or use heat strengthened glass that'll stay in place after it breaks. Generally, this is some kind of optical distortion you're seeing here. It's not in the middle. So we kind of know it's not atmospheric because atmospheric happens in the middle. We also know it's not roller waves because roller waves are going the other direction. So what is it? So we did some analysis on clamping pressure, and it's uneven clamping pressure and way too much clamping pressure on the right-hand side. So I think Dave used MEPLA for this. But yeah, you're clamping this. It's unevenly clamped. It's pushing this in. And you're getting this profile, which is the profile we measured. There's no other way to get that other than overclamping. Oh, yes. The death ray. All right, so this building, it's got curved glass, right? And it's curved as a parabolic solar oven. So it's kind of cool. It's got some things on it. It's reasonably reflective, but it's not super reflective. But glass is by its nature pretty reflective. Oops. So this is the first burn. It burnt down, and you could see they had sort of landscaping here, some plants, some trees, some shrubs, arc mulch. It started the insulation on fire and then destroyed this whole curve. We weren't called in yet. They rebuilt it first. So now it's rebuilt. And then they called us because one of these bushes caught on fire, and they got out there and put it out, and then called us, said, what the heck's going on here? I'm like, well, you built a solar oven, and you've got dead plants there that are perfect tinder, right? So, okay, so thanks, Brian, for coming out and telling us what our problem is. How do we solve it? We want to put a film on there, tell us what film to put on there to make this better, because we're not replacing it again, and we're not going to, go with segmented glass. This has to be curved. So we thought, oh, I'm game to figure this out. I've never put a film on this. I have put film on like diffusion film on glass that has AstroTurf in front of it, because the glass is melting AstroTurf. It's called Turf Guard. I thought, let's try it. I'm always game to try it. But in order to try it, you want to figure out how hot it is and then figure out if it made any difference, right? So we go, we do some finite element modeling, we figure out how hot it is. It's hot enough to catch fire, and there's that center point. So we thought, okay, we know that this is real, and we can't really model the diffusion film. We just don't know how well it's going to work. So we thought, let's go set up some equipment. We'll measure how hot that's getting. We'll put the diffusion film on. We'll measure how hot it gets, and we'll be able to tell if that diffusion film is doing anything or if it's going to work. So we went out and we installed some sensors. There's a little black body there, right in the center point. And as I was hooking this thing up, he noticed he could smell something burning. And he looked down, his jeans had a hole in them. He burnt a hole through his jeans, this death ray. So he ended up getting out of the way and moving the ball a little bit. So we set the ball up. We put, Roxol insulation all over so that it wouldn't burn our equipment up. And we missed one spot, so it burnt our equipment up. So we got back to the office, and the maintenance guy says, your equipment's smoking. I'm like, what? So we run out there and put it out before it caught on fire. So we had 278 is what we're measuring there. And that's pretty close to what we're predicting with our model. We put this diffusion film on, this Turf Guard, just to see if it would make a difference. You see it's sort of opaque. You can see through the glass. It kind of looks like it's dirty glass. It's got tiny little holes in it. And it just makes the light that reflects off really diffuse, but it doesn't matter because it's still a parabolic arc. And so that's, it went from 270 to 250. So that's still too hot, and it's still going to cause a fire. So once we got the diffusion film on, realized that they didn't want to do anything else. Basically just took all the organics off that roof, put a bunch of pavers lapped over top of each other, and put a fence in the death ray zone. If you really want a suntan, you just head out there. All right, I throw this in here. Vacuum insulated hybrids. Where's our last speaker? All right, you should go get him. All right, so VIG hybrids, I get asked on a daily basis because it's my job to keep current on new things and leading edge stuff in the fenestration industry. So it's at least once a week someone will ask me what they should do about VIGs and we should get them. And here we look online and we see incredible numbers. R21 for the Lux wall, Guardian shooting R16.9, just incredible. Your windows are literally going to be more insulative than your wall. Holy cow, that's a big step in the right direction for us. But what does it mean? And I'm a very risk adverse person. We got enough IGU failures, something we've done for 50 years. I don't want to step into something else that's new, that isn't going to give me the peace of mind to be able to sleep at night. So in order to do that, I get involved with the ASTM Durability Committee. I start learning about VIGs. I thought, I want to maybe get involved with, but we don't really have a job. So I was talking to Mike Battistel at Cascadia, and he's like, you know what? Let's think about on your house. At the same time, this is my house. My wife is sending me these pictures because I have the most energy efficient windows in North America in my house. They are the old, non-thermally broken, single glazed aluminum flange windows, right? I think they're the worst that you can get. Like a wood window, steel window, anything's better than that in a single glazed. There's no low E coatings. And my wife is telling me, this is the year you're going to get rid of the condensation on the windows, right? I'm not going to stand for it any longer. You got to do something. So my wife's saying, do something. Mike's saying, we want to figure out a way to start looking at these VIG units in a safe environment where we can get back and look at them and figure out how to make them and figure out how to install them in our product and say, okay, I think we got a good match here. Plus, I thought it'd be really kind of a good story to be able to say I went from the worst windows in North America to the best energy performing windows in North America. So if I live in that house for 25 more years, I'll make up for all of the carbon that I burnt with my single glazing over the last 25 years there. So we put them in. This is pretty funny. So they go in. This is the first week anyways. If it's not the first day, it's the second day. My wife sends me these pictures. I thought I told you to get rid of the condensation on the freaking glass. And I said, oh my God, they're condensing? I said, that's so cool. And I'm so excited because it literally means they're better than my walls. Like my walls don't have condensation on them and my glass does. It means that my stud wall with my siding on it is doing worse than my windows. And she said, perhaps you didn't understand what I told you to do. I don't care which side of the window the condensation's on. I wanted it gone. And so it was really cool. We threw in VIGs in triple. So I went all triple. Standard cardinal triple here. VIG on the outside. And you can see the impact. We were just trying different things, just see what happened and just pay attention. So you can see the pillars when it's on the outside. You can't see any pillars inside. Triple. So you can kind of see where the VIGs behave more like a regular triple, right? It's around the edge where you have the edge seal, and it's at some of the pillars. So it's really, really cool. This is all part of the beginning of what will be a multi-year research project. We've got Luxwall interested in using my house to kind of try and figure out how we're going to field measure performance and take some readings. So make my wife really happy having people traipsing through our house taking readings.
Effective dehumidification device for the house.
Yeah.
Because I guarantee you, you're burning plus 60% RH in there. Because I know your ventilation's what? Your furnace running on?
No, my ventilation is the rest of my walls, which are basically lap siding with some paper-faced fiberglass in it.
I would bet you're going to find out that it's more airtight than walls than you think, and you're just living in a high humidity environment.
No, that humidity is all on the outside.
Oh.
None of it's on the inside. It's all on the outside. And what is interesting is, whenever there's sort of a clearer night, you can see the clearer night, you're getting that kind of night sky radiation. And it's Otto?
Right, I think for a reader, can you explain why condensation is forming on the outside of your units?
So condensations are forming on the outside because the insulative value is so good that at night, when you have a clear sky, everything on Earth gives energy to the universe. And when it does that, it gets a little cooler. And so this is so good that it's not any energy from my house, but it's giving energy to the universe, to space, and it's cooling down below the ambient temperature of the air outside. That's a really good thing from an energy standpoint, and it's not great for making my wife happy, but I'm really stoked. I mean, this is proof that it's better than my walls, for sure. And it gives us something to look at in terms of, where we're going to focus our sort of research moving forward, right? Pillars, perimeter, and where are we going to put this? Maybe if we sell to people that want to see out in the morning on a clear day, maybe we go back to doubles. Maybe we don't do triples, right? All this stuff. I think we should put a double in there, Mike, just to see. It's so much fun learning new things. Speaking of new things, right? We're doing a research project right now on thermal performance of spandrel assemblies, and we're actually incorporating Lux walls and a few other VIGs in that to see how you model and how close that modeling is to real life by doing full-scale hotbox tests on samples that we're modeling. So we're going to get to that point where we're going to be able to tweak the models to really simulate real life and maybe eliminate some of those weird discrepancies we're seeing between manufacturers and focus in what's really going to give us the performance we need. The new ASTM VIG durability standard is just going out for ballot. It is loosely based on 2190 because we wanted to be, the first draft of the standard wanted to be able to be tested in a lab with test equipment they already had. So when it hits the streets, you can start doing testing. but it's pretty similar to 2190. 2190 is already not an approved standard for testing spandrel glass. Like spandrel IGUs, it says right in 2190, not applicable for spandrels, because spandrels often have opacifiers on them that you can't see if there's dew point condensation, and they're also get a lot hotter than regular IGUs. And if we look at some modeling we're currently doing for the first research project, you can see here, ASTM 2190 tests at 60 degrees C, very hot temperature for a Vision IGU. What we're modeling is 120 degrees C. You can boil water in a spandrel. And so if this is the test we're using to identify durability, and this is what we're really going to see in real life, it's really, for the next few years, going to be up to the manufacturers to develop their own internal tests that really look at durability, because the basic one isn't really going to do it, right? The one that's hitting the streets now, it's going to need to be improved over several iterations to include all the things we really need to make sure that VIGs last forever, which is what I want because they're in my building. And we got the hubs test, but more is to come. So stay tuned. This is like, we're in our first month of our pilot project. We've already learned a ton of stuff, which I haven't even put here. Next time I come back, we'll give you the whole summary.
Will we still be married?
Yeah. Well, yeah, this started a snowballing effect. So the windows, well now, got to paint the outside, got to paint the inside. The window guys, the carpet's all dirty. The window guys have been in here replacing windows, need new carpets, need new flooring, new kitchen. Yeah, so yeah, it's never going to end. I've got time for a couple of questions. Oh, one question. Yes.
When it was giving off the heat on the exterior, was the heat dispersion equal around the pane of the glass, or was it concentrated?
Say again?
The heat dispersion on the outside, like because it was retaining the heat and giving it off, did you have equal heat dispersion on the outside?
This is for the VIGs?
VIG, yeah.
Yeah, no. So the reason you're seeing those patterns is that you are getting convective heat flow through the frames, right? Through the edge seal, through the pillars, more than through the vacuum. And so the patterns you're seeing are a result of that difference. So the edges are behaving more like a standard triple, pillars are behaving a little bit like a standard triple, and in between all those things is behaving like a full-on vacuum space with virtually no heat transfer. Any other questions? Murray, you gotta have a question. Yeah, Anton.
We want to hear you, so just wait anyway.
With all the failures you're seeing and put up that are related to high temperature heat issues,
Yeah.
some of the premature failures I've been seeing, especially on the residential side with fenestration, I could link it back to June 30th,
Yeah.
the heat dome. 45 degree plus ambient temperature. Are you seeing any linkage between this type of environment and things that worked in the past and have been, maybe the failure was 1%, but then it started going up to 5, 6, 7%.
Yeah.
And it's linked to that time frame, and that we should be thinking about different peak load systems.
Yeah, I think we need to start testing at higher temperatures because temperatures are getting higher. There's a golden rule in chemistry that's for every 10 degrees you go higher, you double the speed of the reaction, right? And so if you're hoping that, if you're testing it at 60 and it lasts 30 years at 60, and then you go 120, well, there's an order of magnitude faster. So that means it's not going to last very long. So I think, that's the golden rule. Yes, we need to increase the temperature at which we're accelerating testing things and increase the amount of UV as well. Yeah. Yeah, I know some vacuum insulated glass manufacturers use a 30 times sun, right, to throw enough UV at their samples to simulate like 10 years in service in a few months. That's great, but that's not a requirement. So some do, some don't. It'll be a nice when we get everybody doing the same thing.
I just want to point out that any clients that I've got that have put performance triple and the north side is condensing on the outside, they'd rather have it condensing on the inside like the old days because it's cheaper and easier to clean.
It's literally what my wife said. Yeah. I said, what about the mold? There's black mildew. There's no, didn't cut it. It's funny. It's been real fun. I'm going to run. Thank you very much. If anybody wants to talk to me, shoot me an email, give me a call.
Safe travels, Brian.
Thank you.
Thanks so much.